Now this video is going to be a bit of a longer one because we're going to start to define what transformations of the plane are and then think about how we can use matrices to affect those. So first of all, a definition or just a quick description of what a transformation of the plane is. It's simply something which maps every point, every set of coordinates x, y, onto an image point. And we often use the notation x dash, y dash, or x prime, y prime for that. So basically there's some algorithm that takes every point x, y and maps it to an image point. Now that could be a translation, just where things are shifted horizontally and vertically. So a translation is a transformation which just shifts a point horizontally or vertically or maybe both. In other words, it takes the coordinates x, y and adds a onto x, b onto y. Now a and b could be positive, negative, 0, so it can shift x left or right. It can shift the original y coordinate up or down. And we could do that using matrices, not an incredibly sort of valuable thing to do using matrices, but it is true, isn't it, that we could say, okay, the image point x dash, y dash is equal to the original coordinate point x, y plus the matrix with values a and b. So if we added those together, we'd have x plus a and y plus b. So the image point x dash would equal the original point x plus a, and y dash would equal the original coordinate y plus b. So that's a translation. Now most of our time is going to be spent considering what are called linear transformations. So let's just say we will mainly consider linear transformations. Okay, so linear transformations, and those are ones, so which those of the form where we start with x and y, and we end up with ax plus by and cx plus dy. So you can see that those are both, the image points are both linear equations in x and y. So using matrices, let's try and represent that and see why matrices are useful for producing these. So using matrices, we'd be saying, well, the image point x dash, y dash is equal to some matrix A, B, C, D times the original coordinates there, because that would equal AX plus BY, and this would be CX plus DY. So there we have our image point x dash equaling AX plus BY, and the image coordinate y dash equaling cx plus dy. Now you could come up with just any 2x2 matrix, A, B, C, D. Just whack in any numbers for A, B, C, and D, and you could produce a linear transformation of some kind. But a lot of those we'd struggle to describe exactly what they're doing. So we're going to focus in a bit more on specific types of transformations that we're more familiar or understanding of. And so today in this video we're going to focus in on two types, which are reflections and dilations. So let's just say we can develop matrices for specific transformations by considering, we're going to do this by considering what happens to the points 1, 0 and 0, 1 under multiplication by this matrix here, A, B, C, D. So this is the one that we're saying is producing the transformations. Now, think about the points 1, 0, and 0, 1. If we're sort of relating them to vectors, they're kind of the unit vectors, aren't they? Or on our axes, if we're thinking about the Cartesian plane, we've got the points 1, 0 there, 0, 1 here. So they're kind of unit vectors in each of those directions. And we want to think, well, what happens when we multiply those coordinates by this matrix A, B, C, D? So if I take A, B, C, D and multiply it by this matrix here, which represents the coordinates 1, 0, then what do I get? Well, I get A times 1 plus B times 0, which is just A. And then I get C times 1 plus D times 0, which is just C. So in other words, the transformation that's represented by the matrix A, B, C, D is going to take this point here, 1, 0, and transform it to somewhere on the plane with the coordinates A and C. And if I do the same thing with the other one, A, B, C, D, and I say let's multiply that by 0, 1, then I'll let you do that. We're going to get B times D. So in other words, it's going to take this point with coordinates 0, 1, and it's going to translate it somewhere with coordinates B and D. So why don't we sort of work backwards and say, well, what if we wanted to, for example, produce a transformation where every point is reflected in the y-axis or the x-axis or another line? Where would we be wanting every point to end up, and can we actually use that to get a matrix that will do that? So let's start with reflections, and I'm going to start off first of all with reflecting in the x-axis. Alright, so what I'm going to do is just sketch myself a little sketch here and say, if I started off with the points 1, 0 and 0, 1, and I reflected both of them in the x-axis, where would they end up? Well, any point that's lying on the x-axis won't move at all, will it? So the point 1, 0 will stay where it is, but this point up here will be reflected down to the point 0, negative 1. So the point 1, 0 is not going anywhere, but the point 0, negative 1 is going to, the point 0, 1 I should have said, is going to 0, negative 1. So if we use this idea from just up above, that the matrix A, B, C, D transforms the point 1, 0 to the coordinates A, C, and it transforms the point 0, 1 to the coordinates B, D, then we can actually say, well, the points where these end up are the first and second columns of our transformation matrix. They are the points, the A, C and BD. So let me write that here. Let's say, so this is actually our A and our C. That's our B and our D. And so we can say, let's call this matrix the matrix M. We use M sometimes for reflections, and I'll give it a little subscript X to say it's going to reflect all points in the x-axis. And so the first column, A and C, is 1, 0, and the second column, B and D, is 0, negative 1. Now, you might like to take a moment to convince yourself that if I multiply that matrix by any point in the Cartesian plane, it is going to reflect it in the x-axis. So, take a point, let's say take the point, 5, negative 2. Okay, multiply it by this matrix here, 1, 0, 0, negative 1. If I multiply that by the point with coordinates 5, negative 2, what does that produce? Well, 1 times 5 plus 0 times negative 2 is 5. 0 times 5 plus negative 1 times negative 2. So 5, negative 2 has ended up at 5, positive 2. And all that's happened there is that it's been reflected in the x-axis. So, to try and clarify here, that matrix there that we've developed is the matrix for reflecting any point in the x-axis. We can always use that as a matrix for reflection in the x-axis. Okay, so we're already just past 10 minutes, but like I say, we're going to keep going. It's going to be a bit of a longer one, and we're going to develop some other matrices as well. So what about reflection in the y-axis? So now we're saying we want our starting points here of 1, 0 and 0, negative 1. If we're reflecting those in the y-axis, it's only this one that's going to change, and it's going to go to negative 1, 0. Any point on the y-axis is going to stay where it is. So we're saying the image of the point 1, 0 is negative 1, 0. The image of the point 0, 1 is still just 0, 1. So using these two here as the columns of our transformation matrix, we can say a matrix which reflects any point in the y-axis would have first column negative 1, 0, second column 0, 1, and again you could pick a specific point and just double check that that's indeed what's happening. Alright, let's consider a couple of other reflections and then we'll talk dilations as well. So what if we wanted to reflect in the line y equals x? So the line y equals x is that line there, isn't it? So what happens then to the points 1, 0 and 0, 1? Well, I wonder if you can see that actually they just kind of swap places. They get reflected across that line. They end up in the place that the other one was to start with. So the point 1, 0 ends up at 0, 1, and the point 0, 1 ends up at 1, 0. And so we can say the matrix which produces a reflection in the line y equals x is going to have first column 0, 1 and second column 1, 0. Pick a point and confirm for yourself that that is true. Let's do one more reflection, and that's just the one in the line y equals negative x. So that's this one. So there's y equals negative x. Take our 2 points here, so we've got 1, 0, 0, 1, and they get reflected down to 0, negative 1. And this one here gets reflected across to negative 1, 0. So the point 1, 0, its image is 0, negative 1, and the point 0, 1 has as its image negative 1, 0. So we can say matrix for reflection in the line y equals negative x would have first column 0, negative 1, and second column negative 1, 0. And that's going to take any coordinate point and reflect it across, or give us the coordinates of that point after it's been reflected across the line y equals negative x. Now, hopefully you can see this is pretty sort of neat way of doing things with matrices. Like I say, if you're a bit unsure, pause the video, actually get a point and try it with that specific point. Okay, so that's a whole lot of reflections. Let's just do a couple of think about dilations. So dilations are another type of linear transformation, which are basically stretches, and we're familiar with these from maths methods with things like quadratics and that. We actually do dilations where we say let's dilate horizontally or vertically, so from the y-axis or from the x-axis. So let's start off by saying from the y-axis. So if we're dilating away from the y-axis, that means we're actually dilating horizontally. That makes sense. So let's think about, let's draw ourselves a little sketch here. So y and x, and if I had these points, 1, 0 and 0, 1. Now if I'm dilating from there, let's say by a factor of c, so let's just call our scalar factor c. That means however far anything is from the y-axis, it's being multiplied now by a factor of c. So this point here that was 1 unit, it's now being stretched out to another point. Maybe I should have picked another color there, so it's being stretched away to another point here. The point which was on the y-axis, doesn't matter how much you stretch it or what you multiply it by, it's not going to move any further. But it might help here actually to take another point. What if I took a little sort of square here, the unit square, and I said this is just to visualize, but I said, well, this point here is also being stretched by a factor of c, so its coordinates now are c and 1. So all the points that were on the y-axis are still on the y-axis, but every other point that was off the y-axis has been sort of stretched out. And so I started with this square, and now I've got this elongated rectangle. Okay, so the point 1, 0 was stretched to the point C0, the point 0, 1 didn't move, and so let's use D for dilation. If I've got a dilation, horizontal dilation, then I can say the first column will be C0, the second column 0, 1. So basically what that does is it stretches all the x coordinates by a factor of c, because they're the ones that are being stretched horizontally, but it doesn't change the y coordinates. Okay, and then if I was going from the x-axis, in other words dilating away from the x-axis up or down, that would be a vertical dilation. So let's say if we did that one by a factor, let's say by a factor of d. So let's just quickly sketch what that one might look like. So starting with our points 1, 0 and 0, 1, and maybe also to visualize it a bit better, we'll create a unit square. But basically every point is being stretched in a vertical direction. So we say, well, this point here, whose coordinates are 0 and 1, its y coordinate is going to be affected because we're going to multiply it by d. So it's now going to be 0 and d times 1. So it's been stretched all the way up there from its starting point. We've got this one here that's been stretched up to here, so it's going to be 1 d. But the point which was on the, any point which was on the x-axis is staying where it is. But that square, what started as a square, has been stretched out into a rectangle. So the x, any point on the x-axis hasn't moved, and any point not on the x-axis has its y coordinate multiplied by a factor of d. So this dilation matrix can be represented by 1, 0, 0, 0, d. Alright, a few linear transformations.